Hello friends, after the discussion of various machine cycles of 8085 microprocessor, we will move towards the timing diagrams for the various instructions of 8085 microprocessor. So the first instruction is move RD, RS, simple data copy instruction. So here RD is the destination register and RS is the source register. So operation of this instruction you know very well, okay, and the size of the instruction is 1 byte instruction. Okay, so move RD, RS is a 1 byte instruction, and due to this reason this particular instruction requires only single machine cycle, that is opcode fetch machine cycle for the operation. So obviously it requires 3 T states during the execution of this instruction. So in this case, address of opcode which is available in the memory is given by program counter, and after fetching of the opcode, the program counter gets incremented by 1 to point the next instruction. So this is the typical timing diagram for the opcode fetch machine cycle. So as we have discussed, T state wise the operation of the machine cycle. So in this instruction cycle, first 8085 places the contents of program counter on 80 to 87 and A8 to A15. Then short duration AAD pulse goes high to demultiplex the contents available on 80 to 87, because same lines the processor is going to use for data transmission or data reception purpose. Now in this case, processor is going to read the opcode from the memory. So fetching of the opcode from the memory. So short duration ALE pulse you will find in T1 T state, IO/M bar, and H0 and S1 signals get controlled in T1 state T state, that is H0 equal to 1 and S1 equal to 1, which indicate the opcode fetch machine cycle. In T2 and T3 state, the read bar control signal get controlled by the processor, and after the fetching of the byte or opcode from the memory device will control read bar signal, that is this read bar signal made high by the memory device, which indicates the memory device had transferred the opcode towards the 8085 microprocessor. Okay, so in T3 state the opcode fetching or opcode reading process get completed. So this particular move RD, RS instruction requires only single machine cycle, that is opcode fetch machine cycle. So for example, the instructions like all move RD, RS instructions, that is move A, B, B, C, move D, E like instruction, or we can say that all 1 byte instructions we can consider here. So all addition instruction, subtraction instruction, that is add R, ADCR, SUBR, SBBR kind of instructions. For example, add B, add C, add D, add E, SUBB, sub B, sub C, sub D, SBB E, SBB H kind of all instructions. Then single byte logical instruction, that is rotate left, rotate right, that is RLC, RRC, RAL, RAR kind of instruction. Comparison instruction, CMP-R instruction, that is CMP B, CMP C, CMP D kind of instruction. all increment and decrement instructions and all logical instruction, 1 byte logical instruction, ORAR, that is ORAB, ORAC, ORA, ANAV, ANAC kind of logical instruction. Then DAA, decimal adjust accumulator, no operation. So all these instructions are the examples of 1 byte instruction which requires the opcode fetch machine cycle. Next example, that is MVI A, 35 hex. So typical instruction format you know very well, which consists of opcode field and operand field. So if we put this particular instruction in that format in the opcode field, you will find the opcode for this MVI A, and in the operand field we are going to consider this 8-bit immediate data. So MVI A means move 8-bit immediate data, that is 35 hex in accumulator. Okay, so to store this particular instruction in the memory we require 2 memory locations. Why 2 memory locations? Because this instruction of this instruction size is 2 byte instruction. So it's a 2 byte instruction, so opcode fetch and one more machine cycle is required for the operation, that is operand fetch machine cycle. So total 2 machine cycles are needed to perform the operation. So total number of clock cycles or T states are 6. That is 3 T state for opcode fetch machine cycle and another 3 T states for the operand fetch machine cycle. So in this case in the first machine cycle, address of the opcode is given by program counter, and the program counter get incremented by 1 to point the operand field, that is contents available in the operand, that is 35 hex. So in operand fetch, address is given by program counter. So PC or program counter pointed contents are used to take operand and again incremented by 1 for next instruction. So role of the program counter you know very well. During the execution of the program, the contents available or the address available in the program counter get incremented 1 by 1 sequentially. So these are the few examples of 2 byte instruction, that is ADI 8-bit, add immediate with 8-bit immediate data, ACI add with carry 8-bit immediate data, subtract immediate 8-bit data, ORI, OR immediate, ANI, and immediate. So these are the few examples of 2 byte instruction. So this is the timing diagram for the MVI A35X. So as I said, this MVI A35X requires 2 machine cycle, opcode fetch and operand fetch. So opcode fetch machine cycle for the opcode, or to fetch the opcode for this MVI A, that is 3E. So 3E hex is the opcode for this MVI A. Okay, so in the first machine cycle, processor fetches the opcode from the memory, that is 3E hex. Okay, and the rest of the things you know very well. The PC higher content placed on A8 to 15 and program counter lower or lower order address available in the program counter get placed on 8087. the short duration ALE pulse goes high in T1 state to demultiplex AD0 AD7. IO/M bar made low. S0 and S1 both are 1 1, which indicates the upward fetch motion cycle. In T2 state, T2T state, read bar control signal made low by the microprocessor to read or to fetch the opcode from the memory, that is 3E hex. Okay, and in T3 T state the opcode fetching get completed and the read bar signal made high by the memory device. Okay, so after T3 state, processor will check either this particular instruction requires T4, T5 or T6 T state. Okay, so in this particular period, the unspecified period. Okay, so as processor knows that, or the processor decides this particular instruction does not require the additional T states for the operation, it will jump to the operand fetch cycle. Okay, so operand consists of 35x. Okay, then already the program counter get incremented to point the next byte. Okay, so again the PC lower placed on AD0 to AD7 and PC higher placed on A8 to A15. Again the ALE signal goes high to demultiplex or to latch the PC lower address on latch device. Okay, so after latching, the same lines are utilized for data reading. The status signals S0 equal to 0 and S1 equal to 1 made by the microprocessor. In T2 T state, again the read bar control signal made low by the microprocessor, that is to fetch the byte from the memory. Okay, and the data reading get completed in T3 T state, and this particular read bar signal made high by the memory device to indicate data reading is over. So in this way, this MVI 2-byte instruction requires 2 machine cycles, opcode fetch machine cycle M1 and operand fetch machine cycle M2. Next example, that is MVI M, 8-bit immediate data. So MVI M indicates move immediate 8-bit data in the memory. So here M means memory or M means HL pointed content. So operation of this instruction you know very well. So 8-bit data which is available in the operand field get copied in memory pointed by HL the register pair. So HL register pair is nothing but memory. Okay, so one thing is need to consider here. So to store this particular instruction in the memory, we require 2 memory locations. Okay, so 1 byte for the opcode for this MVI M and another 1 byte for 8-bit immediate data. So this is the 2-byte instruction. So as we discussed in previous example, as 2-byte instruction, processor requires 2 machine cycle, that is opcode fetch and operand fetch. But in this case, obviously 8085 requires 2 machine cycle, opcode fetch and operand fetch machine cycle. But the operation of this particular instruction is, that is 8-bit data writing operation in the memory. So move 8-bit immediate number in the memory, that is memory writing operation. Okay, so as here the size of the instruction is 2 byte, but to perform the operation of this MVI M, 8-bit, processor requires 3 machine cycles. It's a 2-byte instruction, so opcode fetch and operand fetch machine cycles for the operation, but the instruction is going to write a data in the memory pointed by M or pointed by HL register pair, and due to this reason one more machine cycle is required to store a 8-bit immediate number in the memory pointed by HL. Okay, so memory write machine cycle also required to perform the operation. So total 3 machine cycles get utilized during the execution of this particular instruction. So therefore total 3 machine cycles are required. So this is the timing diagram for this MVI M, 8-bit data. So first machine cycle, that is M1 machine cycle, that is opcode fetch, that is to fetch the opcode for this MVI M. Okay, so opcode fetch. Second machine cycle for the contents available in the operand field, and one more machine cycle is required that is memory write, third machine cycle, M3 machine cycle, to write a data in the memory. So in this particular memory write machine cycle, the contents available in L register get placed on AD0 to AD7, and contents available in H register get placed on A8 to A15. Why? Because HL holds the memory address. Okay, so for writing the data in the memory, HL register pair holds the memory address. That's why the L register content placed on AD0 to AD7 and H register contents are placed on A8 to A15. Again, the short duration ALE pulse goes high in T1 T state to demultiplex A0 to A7 with D0 to D7. Okay, so once the lower order address provided by the L register get latched in latch device, same lines are used for data writing operation, that is the processor is going to write a data in the memory, that is data from 8085 data bus to memory device. Okay, so in the second T state, T2 T state, the write bar signal made low by the processor. Okay, and after the completion of the data writing operation in the memory device will control the write bar control signal, that is he will make the write bar control signal logic 1 or high to indicate data writing operation is over. So in this way this MVI M, 8-bit data requires total 3 machine cycle, that is M1, M2, M3, that is opcode fetch machine cycle, operand fetch machine cycle, and memory write machine cycle. One thing is need to consider in opcode fetch cycle, program counter get incremented by 1 to point the operand, and in the second machine cycle, that is operand fetch cycle, again the program counter get incremented by 1. So in this way program counter plays an important role during the execution to fetch the data from the memory. Next interesting instruction, that is DADRP. So DADRP is nothing but double addition, and its operation you know very well. This particular instruction adds the specified register pair with HL register pair. Okay, and we know very well that 8085 is a 8-bit microprocessor, but this instruction is going to perform 16-bit addition, so processor requires more time to perform the operation. So execution time is somewhat more during the execution of this DAD RP instruction. The size of the instruction is 1 byte, okay, but its operation is to add the two 16-bit numbers with specified register pair, that is HL plus specified register pair. For example, if I say DAD B, so B means BC pair, so HL plus BC register pair contents get added, and result we will get in HL register pair itself. So as I said, 8085 is a 8-bit microprocessor, so it requires additional time to complete the execution. So during the execution it utilizes bus ideal machine cycles. So during this particular machine cycle, no any operation get performed. Next instruction fetching gets stopped by not giving read bar control signal or not controlling read bar control signal, and ALE program counter get not incremented by 1. So these are the things are need to consider during the ideal machine cycles. So this machine cycle is similar to memory read machine cycle without read bar control signal and ALE signal. So therefore it requires 3 machine cycle, that is opcode fetch machine cycle, bus ideal machine cycle, and one more bus ideal machine cycles. So this is the full timing diagram for the DAD RP instruction. So opcode fetch machines M1 is the opcode fetch machine cycle, okay, where the status signals S0 and S1 both are 1 1 and IO/M bar made low by the processor in this particular opcode fetch machine cycle, okay. Then program counter higher get placed on A8 to A15, PC lower content get placed on AD0 to AD7. The short duration ALE pulse again goes high in T1 T state to demultiplex AD0 to AD7. In between T2 and T3, the opcode of DAD/RP get transferred from memory IC to instruction register of 8085 microprocessor, okay. Then after the opcode fetching in 4th T state, processor decides whether to move towards the next instruction cycle or either to move towards the ideal machine cycle. So after the fetching of opcode, processor knows that this is the opcode for the DAD instruction. He will decide to move towards the ideal or bus ideal machine cycle, okay. So during this particular M2 and M3, you will find unspecified content on A8 to A15, PC lower contains are same on AD0 to AD7, but in this case in M2 and M3 in T1 T states, ALE signal get not controlled by the microprocessor. So ALE signal, read bar signal are maintained as it is. There is no any change in ALE, read bar, write bar, and here IO/M bar made high, okay. And after the completion of double addition operation or after the 3rd machine cycle, processor jumps to the next instruction cycle. Then the timing diagram for the conditional jump instruction. The syntax for the jump instruction. We know very well. So unconditional jump means JMP. In front of JMP you will find 16-bit address where the processor is going to jump or user want to change the program sequence. So there are two jump instructions, that is there are two categories of branching instruction, that is conditional and unconditional branching instruction. So JMP 16-bit address is nothing but unconditional, and if we consider the conditional branching instruction, at that time we have to consider the instructions like JZ, JNZ, that is jump if not 0, jump if 0, jump if carry flag set, jump if carry flag reset, jump if positive, jump if negative kind of branching instruction. So in this case we are going to consider the conditional branching instruction. Okay. So in case of conditional branching instruction, if the condition gets satisfied by the microprocessor, so if I say the instruction JZ 16-bit address, JZ 16-bit address, so JZ means jump if 0 flag set, that is processor is going to check the 0 flag bit. If he detects 0 flag is equal to 1, that is condition is true or satisfied condition. So at that time it requires 3 machine cycle, that is first machine cycle, that is opcode fetch, second machine cycle, that is which consists of lower order address operand fetch, and third machine cycle which consists of higher order address one more operand fetch machine cycle. So all jump instruction size is of 3 byte. Okay, and if suppose the condition goes fails or not satisfied, it requires 2 machine cycles, because in the second machine cycle processor will check the condition of the flag bit. Okay, if the condition is not true, then the processor skips the current machine cycle and he will jump to the next instruction cycle. Okay, so if the condition not satisfied, it requires 2 machine cycle, that is first machine cycle the opcode fetch, and second machine cycle, that is operand fetch machine cycle. So after opcode fetch cycle 8085 starts, next memory read cycle. There is a slight change in the operand fetch and memory read machine cycle. The timing diagram for these 2 machine cycles are same. Only the thing is that in case of operand fetch, the address is given by the program counter, and in case of memory read, the address is given by the instruction. So during this period, flag bits are checked by the microprocessor. If it is true, then he will proceed for the next read cycle, and if it is not true, then program counter content get incremented by 2. Why 2? Because after 2 byte next instruction starts. Okay, that means 8085 skips the current 2 machine cycle to start the new instruction cycle. Okay, so PC content get incremented by 2 and start opcode fetch cycle for next instruction cycle. For example, D800, JZ D800. So JZ means jump if 0 flag set. Okay, so the second machine cycle, he will check the 0 flag bit. If the 0 flag is set, then he will change the program sequence starting from D800. That is, this D800 get loaded in program counter and execution will start from D800. If suppose condition goes fails, that is, if suppose 0 flag is not equal to 1, that is, if suppose 0 flag equal to 0, then he will skip this JZ instruction by incrementing the program counter 2. Why 2? Because of the 2 byte, that is, this is 1 byte and another 1 byte for this D8. So if we put this JZ instruction in the instruction format of 8085, in the opcode field you will find the opcode for this JZ instruction, that is CA hex. CA is the opcode for the JZ instruction, and in the operand field you will find the D800. So size of the instruction is 3 byte. Okay, 1 byte opcode and another 2 byte for operand, that is lower order address 00 and higher order address D8. So another 2 bytes for D800. So total size of the instruction is 3 byte. So in case of satisfied condition, 8085 requires 3 machine cycles for this JZ instruction. So the timing diagram for the satisfied condition, the same for the timing diagram for the unconditional jump instruction. Unconditional jump instruction means processor will not check the flag bits. Okay, so this JMP 16-bit address is the unconditional branching instruction, unconditional jump instruction. So during the execution of the JMP, 8085 will not check the flag bits. Okay, directly he will change the program sequence starting from the address given in front of this JMP instruction. So this is the timing diagram of jump instruction or conditional address when condition is true or satisfied condition. So in case of satisfied condition, he requires 3 machine cycles: opcode fetch machine cycle, operand fetch, and operand fetch machine cycle. In the opcode fetch, the opcode for the jump instruction get fetched from the memory. In the operand field, PC higher content placed on A8 to A15, PC lower content placed on AD0 to AD7, short duration ALE pulse goes high to demultiplex address and data bus. In T2 and T3 T state, the read bar signal made low, okay, to fetch the address. So lower order address fetched. From the memory. Okay, then in the third machine cycle, the PC lower content placed on AD0 to AD7, PC higher on A8 to 15, and higher order address which is available in front of the jump instruction get fetched from the memory by controlling the read bar signal. And again finally, after reading the higher order address, this control signal made high by the memory device to tell to the processor data transfer is over. So in this way, one thing is that in this particular timing diagram, processor always fetches the lower byte, that is lower order address, and then higher order address. Okay, so in this way, during the execution, program counter get incremented thrice. In first machine cycle, M1 machine cycle, PC is equal to PC plus 1. In the second machine cycle, it is also get incremented by 1, and in the third machine cycle, it is get incremented by 1. Okay, and then address is given to the program counter. So this is the timing diagram in case of satisfied case or true condition. So if we consider the previous example, that is JZD800, okay, JZD800, that is if suppose 0 flag is equal to 1, condition is true, then the address given in front of JZ, that is D800 placed here, and program sequence get changed starting from D800. So D800 get loaded in program counter and execution will start from D800. And if suppose condition is not satisfied, so upward fetch machine cycle is as it is. In the second machine cycle, memory read machine cycle, so during this particular T state, that is T2 T state, the processor will check the condition is true or no. If suppose 0 flag is not equal to 1, if suppose 0 flag is equal to 0, as per as the previous example is concerned, that is JZD800, jump if 0, but if suppose 0 flag is equal to 0, that means the condition is not true, then the program counter get incremented by 2. Why 2? Because of 2-byte operand field. Because after 2 memory locations, microprocessor finds the next instruction cycle. Okay, so here if suppose condition is not true, then PC get incremented by 2 and he will jump to the next machine cycle for the execution. Next instruction, that is memory device related instruction. Store instruction, that is STA 16-bit address. For example, suppose STA D100. So size of the instruction is 3 byte. Okay, so in the opcode field you will find the opcode for this STA, its opcode is 32 hex. Okay, and another 2 byte for the operand content or this address 00 and D1. Okay, so as the 3 byte instruction, we require 3 memory locations to store this instruction in the memory. So suppose this instruction is stored in the memory starting from C000. Okay, so at first location you will find 32. At next location C001 we are going to store 00, and at next C002 location D1. So total 3 memory location because of the 3 byte instruction. So as the size of the instruction is 3 byte, he requires 3 machine cycles. Okay, that is opcode fetch, operand fetch and operand fetch. But the operation of this instruction is storing of accumulator content to memory device or specific memory location in the memory. Okay, so storing means data writing operation. So one more machine cycle is required to write a data in the memory, that is memory write machine cycle. So total 4 machine cycles are required to perform the operation for this STA instruction. So opcode fetch cycle 4 T state, opcode is 32, operand fetch cycle with 3 T states with 00, third machine cycle again operand fetch with 3 T state for D1, and one more machine cycle memory write machine cycle with 3 T state to store a data from accumulator to memory location D100. So in the after fourth machine cycle, processor is going to store a data in the memory. So this is the full timing diagram for this STA instruction, STA D100. So first machine cycle M1, that is opcode fetch machine cycle. So here the PC, so during the execution we know very well program counter holds the address of the memory locations. That is, suppose processor is going to execute the program starting from C000, and suppose starting from C000 this instruction is stored, so 3200D1. so program counter holds the address of the program, or starting address of the program. Okay, so in the opcode fetch cycle, IO/M bar signal made low. Okay, S0 and S1 both are 1 which indicates opcode fetch machine cycle. Then PC higher, that is C0 placed on A8 to A15, and PC lower means 00 placed on AD0 to AD7. The short duration ALE pulse goes high in the T1 T state to demultiplex AD0 to AD7, that is address and data lines demultiplexing purpose. Then to fetch the opcode for the STA instruction, its opcode is 32x. So read bar signal made low in T2 T state. Okay, then after reading of the opcode from the memory, program counter get incremented and read bar signal made high. Okay, after fourth T state he will jump to the next machine cycle, opcode fetch machine cycle. So here program counter get incremented by 1. So 01 loaded on AD0 AD7, and C0 higher order address, that is PC higher, placed on A8 to A15. Then operand content get transferred from the memory device to the data bus, that is 00. In the third machine cycle, operand fetch, the higher order address, that is D1, get fetched from the memory by incrementing the program counter, that is C0 and 02. In this case also short duration ALE pulse goes high to demultiplex address with data lines. Again read bar signal made low by the processor to read the byte from the memory, that is D1. And finally after fetching the memory location D100, he will jump to the last machine cycle, memory write machine cycle, fourth machine cycle. So in this case program counter get not incremented by 1. So here C0 and 02 are maintained as it is. Okay, then control signal write bar made low in T2 T state, okay, to write a data or to store a data from accumulator to memory location D100. And after data writing operation, the write bar control signal made high by the memory device to indicate data storing operation or data writing operation is over. So in this way, as the size of the instruction is 3 byte, 1 byte for STA, that is 32, and another 2 byte for D100, 3 machine cycles are required, but due to the operation, that is storing operation, 1 more machine cycle is need to consider to perform the operation, that is memory write machine cycle. So total 4 machine cycles are required to perform the operation. So instruction cycle of this STA consists of 4 machine cycles.